And let's move to the next speaker. So the next speaker is Sergiu Clima from IMEC. This is Leuven in Belgium. IMEC is a partner of our Intersect project. So IMEC is involved both in these ferroelectric topics, but also in the PCM one. And so today, Sergiu will start, I think, with the ferroelectric one, but also give some anticipation of what we will tackle also on the last session on Friday morning. So, Sergiu, please.
Thank you, Arrigo. My microphone is on? Yeah? Yeah. Okay. Okay, good. Thank you. Many thanks to Pablo and his team for this prison break workshop, as I call it. We are breaking from the COVID prison, I guess. So let me give you a short introduction what we were interested in the ferroelectrics of hafnium oxide, hafnium zirconates, and the family. And this time I will go more less into the devices or electrical measurements and more into atomic picture. So we are looking more specifically for the switching mechanism, what might be happening in the these fluorides, ferroelectrics. Later on, I will investigate a little bit on the switching dynamics and just a rough guesstimation what is the time for the switching and some interesting observations. So, well, you've heard today already a lot about the FIFETs and why they are interesting in and how they look like. But the more interesting to me, for example, was how those atoms shift in the material itself in order to give this polarization switching. And I will focus on two main mechanisms that go slightly different ways. But then later on, I'll go into the speed for this switching. So we already heard today that this switching happens at speed of sound. But okay, it's the propagation that goes at speed of sound. But before propagating, we have to have the nucleation first. And then I will show you some ab initio simulations on the differently doped hafnium oxide and so on. How do we do it? We use density functional theory. We use non-elastic band for the kinetic barriers for switching. And we do ab initio molecular dynamics for the switching dynamics. And we use periodic electric fields to get the polarization. So let's focus a little bit on the mechanism themselves. And here we can have the switching itself, we can have it go in two different directions. So one direction, which I call it PBCM mechanism. So this is the symmetry of this centrosymmetric position where the oxygen atoms jump across a hafnium plane. And here you see the animation. This switching mechanism shows the characteristics of a perfect Landau switch in the sense that you can use the Landau equations to describe the switching. However, the barrier height itself, it's slightly larger than for the usually accepted in the literature mechanism, which is the P42 NMC, as I call it, which is the symmetry of the centrosymmetric structure, the tetragonal structure at the central position. And here you can see that the oxygens actually switch between two hafnia planes. And since this barrier height is smaller than the previous one, usually this is considered as the ferroelectric switching mechanism. However, I found some interesting things there that I would like to share with you. So first of all, we have some non-Landau switch potential energy profile. But let's see what ab initio molecular dynamics have to say about this kind of switching. And for that, I did some interesting molecular dynamics, so all at DFT level. What you will see here is basically these two ferroelectric domains. One is in the center of the supercell, another one is across this periodic boundary here. So half of the domain is here, half is there. And this switching will happen at this 7,000 femtosecond time point, whereas the second domain will switch at the 10,000 femtosecond point. And you see that the polarization will go from up to 0 and then to polarization down when we have the electric field applied anti-aligned to the polarization itself. So this is what I would call classical ferroelectric switching. We put anti-aligned electric field to the polarization, and we have the two domains switching one and then the second one. And my animation should start. Unfortunately, it doesn't. Can we have somehow it playing? Okay. It's not visible here. Maybe it's only visible online. Well, the drawback of PowerPoint and animations, I guess, because we don't see the animation here. Well, in any case, what you should see here is that the atoms, oxygen atoms, are being driven by the electric field, and in this case, they go up. And first, it goes the first domain. Second, it goes the second domain. We annihilate the total polarization first, and then the second domain gives us the polarization down. And then this is full switching of the both domain. The problem with this mechanism is that afterwards it goes over a smaller barrier, so the oxygen will shift in between the domains, and then this mechanism will lead to ionic drift. So these oxygens will go up, 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 and up. And actually, after this data point, which I did not go beyond, we get complete meltdown and ferroelectric, well, the dielectric breakdown and melt of the material because the temperature goes way too high. But this is because I chose a very high electric field for this high barrier to see it switching. So what happens next? And next we have to jump already across a smaller barrier. Here we have the polarization already aligned to the electric field, and the oxygens will go down in this case, so they will switch in between two Hafnia planes, metallic planes, and we can see the animation. First it goes with the tetragonal mechanism, which has a low barrier, but then the polarization switches from the plus P to the minus P. And then we have some interesting things going on there, like, for example, half of a unit cell shift. So the dipoles already switched to the next arrow of atoms. So the tetra-coordinated oxygens become three-coordinated and three-coordinated tetra-coordinated. And all these changes in the material lead to the absolutely correct behavior of the total polarization change. So it's quite difficult to understand it by looking at the system, because in the end we end up with a completely centrosymmetric system, no polarization. But from the ferroelectric change point of view, this slope is the expected slope, and this is a valid ferroelectric switching going over a smaller barrier. So this could well happen in the material as well. However, in this experiment, we see that it annihilated the polarization. Well, and then we can give freedom to our imagination, and we can speculate that this could be one of the mechanisms for interpreting the pinched loops and the wake-up mechanism. So, for example, if we say that first we have this tetragonal, and then afterwards the other mechanism, then we could, in principle, explain one possible mechanism to explain these pinched loops and the wake-up mechanism. That in the end will get only one mechanism active. Well, so choosing one of those two mechanisms, we look more into the dynamics of the switching. So we do over and over different models, different ab initio molecular dynamics, and we calculate how long of a time it takes for the switching to start. So basically, we look at the nucleation times. And each of those statistical boxes is in the range of 9, 10 ab initio molecular dynamics runs, and all this for different electric fields. You can see that the lower the electric field, the wider spread in time, and the higher the electric field, the more deterministic the switching nucleation is. And here I plot the median data points to show that we have quite an exponential behavior of the switching, which fits rather well at this high electric fields arrhenius behavior. We do the same for the different temperature of the material, and we see the same exponential behavior. Whereas for different materials, and in this case, I should say that we did not relax the strain, because, for example, if we substitute the zirconium for hafnium to have the hafnium zirconate, or if you put doping of silicon or oxygen vacancies, the strain systems in these systems will be different. So there will be a large difference compared to what I have here. Nevertheless, it's interesting to see that as we expected from the nudge elastic band calculations before, the oxygen vacancy or silicon doping, they break the symmetry in the system, and therefore the switching occurs in small steps, not all oxygens at once, as you should have seen the animations before, but they go one oxygen after another one, and then we have a faster switching when we have defects, and faster switching when we have higher temperature and higher fields. This is intrinsic behavior of the bulk of the material, not considering the grain boundaries and the other extrinsic factors, which we did not consider in this work. Well, we tried also to see whether we can fit it with arrhenius, and in this particular case, at high electric fields, they do fit the arrhenius behavior, but then we have strong departure from arrhenius at lower electric fields. And this is quite known from the other memory out there, where the arrhenius behavior is quite approximate. Nevertheless, we can try to fit to an arrhenius behavior the switching of these ferroelectric materials. And that's what I've done on this chart. So what you see here are the high field and the high temperature data points in the blue dots. And then we could fit arrhenius surface, which is shown with ISO lines for a power of 10 in nanoseconds. And we are interested basically to see what would happen at room temperature at realistic electric fields, which I do not, I'm not able to simulate in molecular dynamics, because even for this single data point, it took like million core hours to simulate. And that's why we have to extrapolate, fit the arrhenius and extrapolate what happened at those lower field and lower temperatures. So my colleagues took some measurements on FIFET by doing some stress and measurements on the ferroelectrics. But what you can see on these charts is first for the paraelectric hafnium oxide. So the material is given longer stress time, and then it traps more and more charges. So you see this in the change of the threshold voltage of the transistor. But then the longer you wait and measure what happens to the threshold voltage, then you see the detrapping. So this is the paraelectric hafnium oxide behavior, and this is the ferroelectric one. So basically, as Johannes just told you, you have to wait for some time for the detrapping to get out in order to see the polarization component there. And here you can see that indeed for the microsecond range you can see the polarization already. But as first speaker Sven from Global Foundry said, well, these devices, they have issues like, for example, RC delays, and then you have all kind of percolation path physics that are not accounted here, so keep that in mind. Well, Johannes already discussed a lot about the trade-off between the charge trapping and the polarization, and they counteract each other. But we could say that our measurements were quite lousy in the sense that the experiments were slow. And we measure in the range of microseconds. However, our DFT extrapolations show that we should be in the range of nanoseconds instead. And for that, we have to keep in mind, we have discrepancy because we don't have percolation path on the ferroelectric not accounted for. And our PhD student had a nice model for that. We don't have RC delays very small, so in principle, the differences can be accounted for. And here I collected some state-of-the-art measurements in the Purdue group of PDEA, where they have measurements of the range of nanoseconds indeed. So our arrhenius extrapolations are quite in line with the state-of-the-art measurements of the switching speed of these materials. Let me go about some interesting observations that could be attributed to the fatigue mechanism, for example. So if we simulate a model that has a cubic supercell, then we constrain the material and it cannot wiggle. So as you'll see later on in elongated supercell model, and we cannot go too high because then simulation time increases too much. So I took this 10 by 1 by 1 supercell of the ferroelectric material, and we do some ab initio simulation. Let's try, maybe this animation can work at least for the online audience, if not for us here. Well, unfortunately, the animation is not working. But what you can observe in this simulation is that at certain point, the polarization in this ferroelectric material rotates 90 degrees. So here it's perpendicular to the in-plane, let's say X direction. And at certain point in time of the ab initio molecular dynamics, it rotates 90 degrees. So it rotates parallel to the X direction. And afterwards, it actually transforms into a monoclinic dual grain model. I was quite intrigued by this simulation, but then we found that there are some experimental evidence for this polarization rotation of 90 degree, and also there is an initio work where they also witnessed exactly this type of 90 degree rotation for the ferroelectric domain. So in principle, we can envision that this kind of 90 degree rotation of the domains could be happening while you switch many cycles, and then you lose the polarization because some of the domains switched orientation, or they switched to the monoclinic phase. And this is basically showing what happened to the end of the simulation, where the ferroelectric orthorhombic phase switched to the monoclinic one. So here we have a grain boundary, another grain boundary, and we have 2 grains of monoclinic, which is not ferroelectric anymore. So this is very realistic mechanism that will happen after many billions of cycles, and we'll lose the orthorhombic phase, and we get more and more monoclinic phase in case we have some monoclinic nucleus to grow, for example, or the material, the ferroelectric material is not clamped enough to hold the orthorhombic phase and not fall into a much lower energy monoclinic phase. Well, we also did some strain simulations on these rotations. So we start with the parallel perpendicular, with the polarization perpendicular to the surface. It's shown in blue. And then if we apply tensile strain, it switches rather fast into the parallel to the surface orientation of the polarization, shown with the orange time lines. And then at the end of the orange bar, it switches into the monoclinic phase. So as you can see, when we apply a compressive strain, the perpendicular polarization, it's more or less on the same timeline, but the parallel to the surface lifetime of the polarization is much shorter than in the case of the tensile strain, and then afterwards it goes directly into the monoclinic. So this shows that the strain will have a great influence on whether you get disappearance of the polarization, so fatigue mechanism. Eventually you can think of it as wake up, for example. If it's parallel to the surface, then it becomes perpendicular. That could be happening during the wake up phase, for example. So to conclude, there are many mechanisms for ferroelectric switching, but they can be categorized in 2 classes. So I say one is the ionic drift mechanism. So it's higher barrier, so eventually it could be a step limiting. However, the tetragonal mechanism P4-2NMC should be faster because the barrier height is smaller, and the mechanism itself is rather complicated. The nucleation of the switching at high field and high temperatures, it's quite arrhenius-like. If we have dopants defects, they will switch faster. Strained hafnium zirconate shows slower switching, but then question mark, what happens when you release the strain on that system? We can have phase transformations, and those polarization rotations or phase transformations or 90-degree rotation of the polarization, they can account for fatigue mechanisms, and especially the transformation to the monoclinic phase will be one of the main failure mechanisms for this ferroelectric material. Well, that being said, I would like to advertise a bit on the upcoming SISC talk, where I will try to explain what the experimentalists see in the ferroelectric. So if you have an applied electric field where you measure the capacitance, or you don't have an applied electric field, the capacitance on the ferroelectric is different. And I would like to see what happens in ab initio when we apply some electric field, and we can explain the capacitance from the change in the dielectric response of the material. So in other words, dielectric constant is not constant, it's a dielectric response. Well, I guess that puts the end to the ferroelectric session.